All right. Hello. So I'm here to talk a bit about the security of virtualization. We've seen quite a lot of these competing claims. I'll just leave these up for you to read. So the question I'm maybe going to think about today is who's right? Are containers as secure as virtual machines? Are they not as secure now, but are they catching up quickly? Are they both so insecure it's really not worth bothering to think about? So I'm going to try, rather than just answering these questions, I'm going to try and equip you with the tools to assess these questions for yourselves. And I'm going to talk specifically about 3 different free software virtualization technologies, Xen, KVM, and Linux containers. I'm going to compare the risk that somebody will be able to break out of one VM into another, or out of one container into another. I should say that much of the legwork for this talk was done by my colleague at Citrix, George Dunlap, and the entertaining zombie analogy you'll see later is entirely his. So the first thing to talk about is security and risk. People often talk about things being secure or insecure, but this isn't really a binary category. A system which is insecure is really just one that's quite easy to break into, and one that's secure is hopefully one that's harder. If we start thinking about this in terms of risk, it makes it clearer that it's a spectrum. A secure system is a system which has a relatively low risk of being broken into, and an insecure one is a higher risk one. So what is this risk? Where does it come from? So in our particular scenario here that I'm going to be considering, we're talking about virtual machines or containers as our trust domains. But in general, we're trying to evaluate the risk of somebody bypassing the protection mechanism, in this case the virtualization layer, and accessing data or resources in other VMs or other containers, or maybe even taking control of the whole system. A source of this kind of risk in software is generally vulnerabilities. That is, a vulnerability is a weakness, a bug somewhere in the interface or in the configuration, which an attacker that has control within one trust domain can take advantage of to do things in another trust domain that they're not supposed to be allowed to do. The code or technique that an attacker actually uses to take advantage of a vulnerability is called an exploit. You've all heard of those as well. If there's a vulnerability and the attacker knows about it, then the attacker can get into your system. And if there's not a vulnerability, or if they don't know it, then the attacker is foiled. So the virtual break-in requires the existence of a vulnerability and the right combination of luck and knowledge on the part of the attacker. Vulnerabilities are really key. A vulnerability in software is a mistake. This could be a mistake in the code itself or in the configuration. I'm going to be focusing mostly on software vulnerabilities in this talk, since most of the systems I'm talking about have at least tried to make the configuration vulnerabilities less easy to make. So I'm going to consider an example of a vulnerability. You've probably all seen this cartoon already. This is a fairly simple one, which actually arises, I think, originally from a design error in the TLS protocol, because it's got 2 length fields in these heartbeat packets. Then, of course, that gave the opportunity for a programming error in OpenSSL, which was the dominant implementation of TLS. So the risk we're interested in is the probability that an attacker knows of an exploitable vulnerability. So now it's time to come on to my analogy. So you and your motley crew are the last remnants of humanity, as far as you know. You're going from place to place, living on the remnants of the old civilization. You stay in one place until you use up all the resources in that particular place, and then you move on. So all you have to do, so these are the rules that zombies work by. So all you have to do is find somewhere to hole up for the night, board up all the doors and all the windows, secure it all properly every night. If you leave a single crack open and the zombies find it, then that's the end of the story. They'll all come in and eat you. So it's not that hard to secure any given door or window. But you're just human. You're tired, stressed, in a hurry, hungry. Not everybody is the best carpenter. You don't get to choose who's with you in the zombie apocalypse. Despite your best efforts, You've occasionally woken up in the morning to find things that weren't properly nailed shut. By luck, the zombies didn't find it yet. So what kind of building do you want to hole up in? What are you going to want as your base and night shelter? Well, every door or window is an opportunity to make a mistake. Every mistake is a roll of the dice. Do the zombies find it before you do? The survival of the human race depends on having few mistakes and being lucky with the mistakes you do make. For small probabilities, the risk of having a single open door or window scales linearly with the number of openings that need to be secured. So you're going to be looking for a building with few windows. Secondly, you're going to be looking for a building with small, simple doors and windows that are easy to secure. The bigger and fiddlier the doors and windows, the more difficult each one is. We're not all carpenters, so the larger the window, the more risk that when trying to secure it, something will get screwed up. Finally, if possible, you'll be looking for a building that allows you to have multiple layers of protection. This is called defense in depth in the security community. Say if you can secure the fence around the building and the building itself, then to eat you, the zombies need 2 mistakes. And if they get through the fence but not into the building, hopefully in the morning you can clear out the grounds and repair the fence. The chance of having 2 unsecured doors is exponentially smaller than the chances of having just 1. So how does this apply to software? Well, every element of every interface is an opportunity to make a mistake. The risk we're concerned about is the risk of a vulnerability in the interface to the virtualization software, if we're considering virtualization technologies. In every corner of that interface, every argument to every function, every register operand, every interaction of internal state is an opportunity for a mistake that will allow an attacker to break through that interface. This is what's called in the security community attack surface. And now we get to my key point. The fundamental difference between a hypervisor and a container is the interface that the virtualization layer provides. A hypervisor provides an interface similar to that of hardware. So it'll give you memory and page tables, but you have to make your own operating systems. It will give you a disk with block read and write, but you have to make your own file systems. It will give you a network card that can send packets, but you have to make your own TCP streams. This interface has a fair amount of opportunity to screw up, and as we'll see later, there have been a number of screw-ups. Both KVM and Xen do a lot of instruction emulation in the hypervisor, and the x86 instruction set is not really that simple. Well, ARM is much better, and anyway, because of ARM's better design, we don't need to emulate to do virtualization on ARM, but that's a bit of a side note. Xen has about 40 hypercalls, most of which are not usable by normal VMs, well, supposedly, but they are there. But if you compare this to the interface you get from the Linux kernel, it's quite a different picture. Kernel gives you file systems with files, directories, seek, fstat, read, mmio, and aio. How many different kinds of sockets can you create? How many different IPC mechanisms are there? How many ways to read and write to a file or network stream? All of them with lots of internal state and corner cases which need to be handled correctly. There are just a lot more opportunities to make a mistake in the Linux system call interface, and as we'll see, a lot more mistakes are made on a regular basis as a result. Well, that's a theory, but as we know, it's often the case that theories turn out to be wrong. Do we have any actual evidence that the Linux system call interface is less secure than a hypervisor interface? And in any case, does the difference in security matter? Maybe Linux has really good security for average people, and hypervisors have a crazy level of security for people like the NSA. Or maybe, like Theodor Rath said, they're both so insecure that it doesn't really matter which one you pick. So George went through the CVE vulnerabilities for the last year, for 2014, in each of 4 projects: Xen, KVM, QEMU, and Linux. QEMU is relevant because the standard KVM setup has QEMU as an integral part. And so for each one of these vulnerabilities, he and I considered, if we were running a system configured to be reasonably secure, how would this vulnerability have affected us? And if so, how? So I need to explain a bit. These are the results we got. I need to explain a bit about what I'm comparing here. To make the figures comparable, I had to pick a configuration and usage pattern for each of the systems. So, for example, I had to assume what kind of CPU we were running on. I assumed we were using an Intel x86. I had to assume what kind of setup we were providing to the guest, and I assumed that the guest was a separately administered, vaguely general purpose operating system. Mostly because that's more comparable, that's what the Xen and KVM provide. I have assumed that our enemy has already gained control of the guest, either because they're actually our customer, maybe if we're a hosting provider, or because they found a vulnerability in some application software on the guest and have taken it over. I've mostly counted vulnerabilities which would gain the attacker control of the system, or correspondingly denial of service or information leak bugs relating to the whole system. So I haven't considered bugs where they're supposed, for example, to be an internal security interface which can be breached. I've only counted bugs that get you all the way to control of the system. So these are the vulnerabilities that a cloud hosting provider, for example, would be worrying about. For other scenarios, you might get different numbers, but I had to go through and make some set of assumptions while I was categorizing each of these bugs. But certainly the problem I'm analyzing here is one that Xen, KVM, and Linux are all touted as approaches to solving. So along with a few other detailed assumptions that I won't go into, allows me to compare the number of vulnerabilities in these three scenarios where each system is providing similar functionality. You can see I've provided ranges for some of these numbers. That's because it's sometimes a bit difficult to tell how bad a particular vulnerability is. You read the advisory and it says, well, a privilege escalation has not been ruled out. And then you go and read the patch and you think, well, yes, well, do I count that as a privilege escalation or don't I? So in cases where I wasn't entirely sure, I've counted it as maybe, which you can see reflected in the table. So the figures here, to an extent, speak for themselves, but I wanted to look at some of the vulnerabilities in more detail because it's quite illuminating. So let's start with one of the Xen ones. The juiciest one is Xen Security Advisory 87, CV 2014-1666 from January last year. So there are two hypercall suboperations called FISDevOp Prepare and Release MSIX, which you will probably have never heard of. They're supposedly for the privileged system software to do interrupt setup, but they were missing the privilege checks. So any PV guest could mess about with the interrupt routing. The effect of this might vary, but generally the host would crash. So I haven't counted this as a privilege escalation because the XSA 87 advisory says this is probably not possible in this case. We don't know that for sure, but it seems likely. So that's a very simple and obvious kind of mistake. Let's move across the table and look at one of the KVM QEMU bugs. CV 2014-8106, which some people have called Cirrus Insufficient Blit Region Checks. This was a missing range check. Hey, stop that. A guest which exploits the bug can write to arbitrary memory in QEMU by doing strange things to QEMU's emulated video driver. And this emulated video card. And this is a problem for KVM because KVM uses QEMU for VGA emulation. Again, this is a very simple mistake. But there's something more interesting going on here. Why is there a VGA emulation anyway? Well, KVM and QEMU provide their guest with an emulated PC. PCs have graphics cards, so there has to be an emulated graphics card. QEMU contains various emulated graphics cards, but this particular one, the Cirrus emulation, is the default one, and it's used in most installations. Xen PV guests do not get an emulated Cirrus graphics card. So this shows the advantage of a small attack surface. If you don't provide a feature, there can't be any bugs in it. It also shows the importance of selecting the best configuration. If we had set up our Xen guest as HVM, it would also have had an emulated PC. That emulated PC has got an emulated Cirrus graphics card provided by QEMU, just like with KVM. So Xen HVM setups are vulnerable to this bug. I haven't done the detailed analysis, but I would expect a Xen HVM system, when configured not to use the privilegely separated subdomain QMU, which is a complicated security feature, I'd expect it to have numbers similar to those we see for KVM plus QMU here in this table. So what about Linux? That's what we came here for, right? To find out the truth behind the container hype. These numbers do look quite bad. Let's pick the top one off the list I got from George. CV 2014-9322, privilege escalation due to SS fault. This is a complicated bug to do with the handling of a particular processor exception during interrupt return instructions. It's a privilege escalation from any Linux process into the kernel, and it doesn't even need any particular syscalls to be enabled. Looks to me like this bug is due to some very complicated and not to say bizarre rules in the way Intel CPUs handle transitions between kernel and user mode. But I'm not an x86 expert, so that's the best I can do as an explanation. Never mind, if I can't explain that one to you, there's probably some more. Let's pick another one. 2014-3153, Futex run queue doesn't ensure different futexes. A futex is a fast mutex. It's an inter-thread synchronization facility provided by and specific to Linux, primarily used by the standard pthreads threading library. The kernel's implementation of one of the futex operations operates on two caller-specified futexes, and it failed to check that the two futexes were different. If they were the same futex, Linux would get its data structures tangled up, and that tangling up then made it possible for exploitation by another futex call. KVM and Xen are not vulnerable to this specific vulnerability, of course, because they don't provide futexes to their guests. But that's kind of missing the point, because they do provide inter-thread, or inter-vCPU, as they call it, synchronization facilities. But they provide very few such facilities each. In the case of Xen PV guests, there's pretty much just Xen's event channels. Linux provides, depending how you count them, maybe a dozen different types of inter-thread or inter-process synchronization facilities. I could think of 8 straight off: futexes, fcontrol locks, flock locks, TTYs, System 5 semaphores and message queues, pipes, named anonymous, AF Unix sockets, signals, and iNotify. Worse, these facilities can be exercised through a bewildering array of APIs, and I speak as an experienced POSIX API programmer, which have all grown up as the operating system has come to be a convenient library of useful functionality. Indeed, we can see this richness and the corresponding risk in this very example vulnerability. In the first submitted patch to fix the bug, the code compared the two uaddr values passed into the function. That is, the two user process addresses for the two futexes. But Linux supports futexes which are shared between multiple processes, in which case the same futex can have different addresses in different processes, and indeed be mapped more than once into the same process at different addresses. So the first draft of the patch didn't properly fix this bug. The problem with the initial bug fix was itself fixed during the patch review. So it just goes to show how much more opportunity there can be for error with a complicated API. So of course we need to take these numbers with a pinch of salt. They're quite small, so there'll be some statistical variation. Whether vulnerabilities are reported depends not only on whether they're there, but also on whether and how hard people are looking. Speaking about the Xen project, we're aware of a few teams' efforts in the last few years to do some fuzzing, auditing, and static analysis, but there's not really any central tracking of this kind of activity, so it's really hard to say which of these projects is looking harder. Finally, I need to point out that my comparison has been of 3 general-purpose containment approaches. They all provide, in the guest, something that looks much like a normal operating system. If you just want to run a specific application, then it's possible to restrict Linux containers. For example, when using Docker, it's recommended not to give your applications root inside the container. Then you get numbers which look a lot more like those of a real virtualization system. Of course, the guest environment has much more limited functionality. You can't run a general-purpose operating system with a full set of management tools and so on, but if you don't need all that, then you're much better off restricting the facilities available to the guest. That reduces the attack surface. But the interface provided to a non-root container guest is still much richer than that provided to a PV Xen VM, and that's still reflected in these figures. So, to summarize, The biggest enemy of security is complexity, and particularly API complexity at security-relevant boundaries. The smaller and simpler the API between your trusted and untrusted components, the better. Linux container systems have excellent management and convenience benefits, but I conclude that they shouldn't be thought of as a tool with security encapsulation as a primary benefit. If I was providing a cloud service for containerized services, I'd want to run them in proper VMs, perhaps one VM per customer, to provide more dependable isolation. So thank you, and I think I probably have some time for questions.
I have a question. Do you have ESX numbers for that?
No.
No,
No,
can you repeat the question?
The question was, do I have numbers for ESX, which I assume you mean the VMware product? And the answer is no. It's quite a lot of work. So if you want to do the analysis, very welcome to.
Any other questions?
Someone?
So you're looking at current data for just last year, but Linux containers are much newer than both Xen and FOSDEM. So in 5 years' time, would we still be having the same conversation, the same data?
Repeat the question.
The question was, so I've looked here at 2014's data. The question was, Linux containers are relatively new, so will we be looking at these same kind of figures next year, say, or in 5 years' time? And the answer is, it's hard to say. A lot of this depends on how much churn there is in the code base, because vulnerabilities sort of get found, like other kind of bugs, and removed. But every time you change the code, there's an opportunity to break it again. So you might want to consider how fast the core security-relevant interfaces in the project are changing. And I haven't done any analysis of that at all.
And of course, containers aren't actually that new. They've been around actually longer than KVM.
Have they? Well, marvelous.
Defense in depth, depending on how it's done, can introduce some complexity to the point when you become sloppy. How do you address this problem?
Yeah, so the question was, defense in depth can introduce complexity, and it can also make you sloppy. And these are both very, very true. So the answer is, when you're deciding whether to go for some kind of defense in depth approach, you should be thinking about how independent the two layers of protection are and how much the existence of one of them is complicating the other. And the other thing is, you need to be very careful to resist arguments which say, oh, this isn't really an important bug because we've got this other layer of defense. And if you're not careful, you can end up making that same argument each way round with both layers of protection and get very sloppy indeed. And to an extent, the bugginess of software in general is, it's a sort of homeostatic system where software is as buggy as we put up with it. And the more pressure you put on to say, no, no, this is too buggy, we need to fix this, the better the software will be. And the more you kind of tolerate bugs, the worse it will be.
When you were considering Linux for computers, were you looking at a stripped down kernel? Because obviously if you've got 5,000 drivers, your attack surface is huge. If you've just got one disk driver, one network driver.
Right, so the question is, did I look at a stripped down kernel? And the answer is, I made some assumptions about which facilities the attacker would have access to in the container. The question was specifically about device drivers, like how many disk drivers you have. So having dozens of different disk drivers in your kernel is actually not that bad a vulnerability, because in any particular setup, only one of those will be running. So attacking the others is essentially not really possible. It is possible to an extent to restrict the arrangements for, so for example, with things like SE Linux and seccomp2, you can try and restrict the set of system calls that your applications have access to try and exclude vulnerabilities in interfaces you're not actually using. This turns out to be, quite a lot of work, because you now need a completely custom set of allowance rules for each individual application. And secondly, for many of these bugs, it doesn't actually help, because the worst bugs are the ones that happen when the arguments of the system call are being unpicked in the kernel to try and figure out what's going on. And that obviously has to happen before the security layer does its checks, because the checks depend on knowing what the system call was about. So often it doesn't protect you. It wouldn't protect you from that Intel SS bug at all, for example. That doesn't even depend on a system call. Sorry? Unikernels. So the question was about unikernels. Well, if you want to run your application in a Xen PV guest, then you can use a unikernel. And that's a good way of running an application in a secure virtualization system without needing a lot of the operating system overhead. It doesn't really, a unikernel doesn't really improve your security compared to running, say, your application on Linux inside Xen PV. Actually, what it mostly does is improve the performance and maybe the deployment and manageability. There's a question over there. So the question was, are there efforts to deprecate some of these interfaces? To a very limited extent, certainly in the POSIX API, there are some interfaces that are being deprecated. But the examples of, for example, System 5 message queues was mentioned, and I'm not aware of anybody who has suggested deprecating System 5 message queues, and there's probably a surprisingly large amount of software that uses it somewhere. This is part of the problem here is coming because the operating system kernel is performing two functions. It's performing a privilege separation function, but it's also providing a library function. It's got an awful lot of functionality in it which is there for convenience, and if you start removing that, it becomes less convenient and harder to port your software to. So I think if there aren't any more questions, thank you very much.